So we're now going to consider the Hertzprung-Russel diagram. With our Hertzprung-Russel diagram, along the vertical axis, we've got the luminosity. So the luminosity is literally the rate of emission of radiation. So this is telling us how quickly our star is releasing energy. Along the horizontal axis, we've got the surface temperature. So remember that the surface temperature is related to the color of the star. This relationship comes from Wien's law, which tells us that lambda max, so that is the wavelength of light for which there's the highest intensity of energy released. So lambda max times T, the temperature, is equal to 2,898 micrometers per kelvins. Now the Hertzprung-Russel diagram is a nice way to show stars, as we can relate the evolution of stars to their position on the Hertzprung-Russel diagram. So we've got a diagonal line down the middle, and this is where all the main sequence stars are formed. So our Sun is a main sequence star. It's around about in the middle of the main sequence. The blue stars are hotter stars, they're larger, and they really have a much higher luminosity. So because they have a much higher luminosity, they're releasing energy a lot more quickly, and so they will burn through their fuel stores a lot more quickly, and they'll actually have much shorter lives than the stars further down in the main sequence, which are releasing energy a lot more slowly. Once a star ends its life on the main sequence, depending on its mass, it will either become a giant, so a red giant like our Sun will, or a supergiant, which is the fate of the heavier blue stars. Once our Sun finishes burning helium in the red giant stage, it will cool down and become a white dwarf. So at that point, it will move to the lower left-hand corner of the Hertzprung-Russel diagram, where it's just releasing energy until it gets so cool that it is no longer releasing energy in a visible wavelength anymore, and we don't see it.